Hello, welcome to my video series of data structures. This is part 2 of Module 7, the union-find data structure. In this video, we will discuss the quick find implementation of the union-find data structure. In the previous video, we introduced the union-find data structure, which is commonly used in applications such as generating random mazes. The union-find data structure, also known as the disjoint-set data structure, organizes elements into groups where each group represents an equivalence class. In the context of a maze, a disjoint set corresponds to a collection of interconnected rooms. The goal of random maze generation is to ensure that the entrance and exit belong to the same disjoint set. This is achieved by randomly breaking walls between rooms, gradually connecting different regions of the maze in a randomized manner. We developed the following algorithm for constructing a random maze. This algorithm is built upon two fundamental operations for the disjoint set data structure: the find operation implemented in line 4 and the union operation implemented in line 8. Specifically, the find and union operations ensure efficient connectivity management within the maze. For instance, when a wall between two adjacent rooms is removed, these two rooms become connected. Consequently, we must also merge the two disjoint sets, each initially containing one of the rooms. To achieve this, we first use the find operation to identify the disjoint set associated with each room. Then, we apply the union operation to merge the two sets. In this video, we will focus on the quick find implementation of the disjoint set data structure. This approach enables the find operation to run in constant time O1, and the union operation executes in O log n time. Suppose that the disjoint set data structure contains n elements. To represent these sets, we use an array A of length n, where each entry stores the label of the disjoint set to which the corresponding elements belong. That is, AI holds the label of the disjoint set that contains element I. For instance, in the example shown here, A3 has a value of 3, indicating that element 3 belongs to disjoint set 3. This scenario represents the initial state of a disjoint set data structure, where each set contains a single element. In our example, set 1 contains element 1, set 2 contains element 2, and so on. Now, suppose we need to merge sets 1 and 2. To merge set 1 and set 2, we update the labels of elements in set 2 to 1, indicating that they now belong to set 1. In our case, set 2 only contains one element 2. So we update A2 to 1. As a result, both element 1 and element 2 are now contained by set 1. It is important to know that we can choose to relabel elements from either set 1 or set 2, as both approaches are valid. However, as we'll see later, relabeling the elements of the smaller set leads to a more efficient union operation. Next, let's merge set 4 and set 5. Since set 5 contains only one element, 5, we update A5 into 4, indicating that element 5 is now part of set 4. From the above examples, we see that the find operation is easy to implement. To determine the disjoint set that contains the element I, we simply return AI. Since this lookup requires only one single array access, the time complexity for the find operation is O1. Given the disjoint sets represented by the array A, calling find3 returns 3, while both find4 and find5 return 4. From this, we can determine that find3 does not equal to find4, meaning elements 3 and 4 belong to different sets. Conversely, since find4 equals find5, elements 4 and 5 are in the same set. Next, we implement the union operation. To merge two sets, suppose we relabel all elements in Si to belong to Sj. We traverse the entire array in line 2 and check whether each element belongs to Si in line 3. If it does, we update its label to Sj in line 4. This implementation requires O(n) time, as it scans the entire array. However, this exceeds the expected O log n time complexity. In the following sections, we introduce its optimizations and detailed time complexity analysis. The primary computational effort of the union operation comes from relabeling the array entries. To minimize this overhead, we adopt two optimization strategies. First, we always relabel the smaller set. This reduces the number of entries that need to be modified. We can keep track of the set sizes to enable their constant time comparison. Second, rather than checking every array entry, we maintain a linked list to store the mapping between each disjoint set label and the elements it contains. We denote this linked list as L. The illustration below depicts the optimized quick find implementation, which includes the linked list L. Each bucket in L represents a disjoint set, and the nodes within the bucket correspond to the data elements belonging to that set. For example, the bucket L1 contains the data elements of set 1, which includes elements 1 and 2. Now, suppose we continue to merge set 3 and set 4 using the optimized smart union operation. First, we compare the sizes of set 3 and set 4 and determine that set 3 is smaller. Therefore, we relabel the elements contained in set 3 to belong to set 4. To find the elements in set 3, we traverse bucket L3. Then, for each node I in the bucket, we relabel AI to 4, indicating that the element is now part of set 4. After relabeling, we update the size of set 4 to 3 and the size of set 3 to 0. Finally, we append the linked list stored in bucket L3 to the end of the list stored in bucket L4, ensuring that all elements are correctly mapped to their new set. At this point, the smart union operation is completed. Below is the implementation of the smart union operation. In line 2, we compare the sizes of Si and Sj and ensure Si is the smaller set by swapping them if necessary. In lines 3 to 5, we relabel each element contained in Si to belong to Sj. In line 6, we append the list of elements from the bucket LSI to bucket LSJ. In lines 8 to 9, we update the sizes of Si and Sj accordingly. With the smart union operation, the number of relabeling steps is equal to the size of the smaller set. In the worst-case scenario, this smaller set may contain up to half of the total elements, leading to a worst-case time complexity of On. However, it can be shown that the amortized time complexity of this smart union operation is O log n. To analyze the time complexity for the smart union operation, we first establish an upper bound on the number of relabeling steps for any given entry in array A. We claim that each entry can be relabeled for at most O log n times. Consider an element I that initially belongs to the set Si, which is being merged with set Sj. With smart union, relabeling of I occurs when set Si is smaller than Sj. After merging, the new set Sij is at least twice as large as Si. This means that after each relabeling, I belongs to a set that is at least twice the size of its previous set. Because the largest possible set contains n elements, a single element set can at most double O log n times before reaching size n. Thus, any given element can be relabeled at most O log n times. For example, consider the merging of set 3 and set 4, where element 3 was relabeled. Before relabeling, element 3 was in set 3, which had a size of 1. After relabeling, element 3 became part of set 4, which had a size of 3. The set that contains element 3 at least doubles after relabeling. Note that each entry can be relabeled O log n times, and we have n entries in total. Therefore, the total number of relabeling steps performed throughout the entire life cycle of a disjoint-set data structure is at most O n log n. Finally, note that we can merge all data elements into a single disjoint set by performing the union operation n-1 times. Initially, each element forms its own individual set, meaning we start with n separate sets. Each union operation reduces the number of sets by 1. Therefore, after performing n-1 union operations, only one set remains. Since all elements can be merged into a single set using at most O n log n relabeling steps, distributed across n-1 union operations, the average number of relabeling steps per union operation is O log n. In this video, we introduced the quick find implementation of the union find data structure. This implementation ensures that the find operation runs in constant time O1. Additionally, the smart union operation achieves an amortized time complexity of O log n across multiple operations, though its worst-case time complexity remains On for a single operation. In the next video, we will explore the quick union implementation, which allows the union operation to run in constant time O1. Thank you for watching, and see you next time.